Good time of the day. Welcome, everyone, and thank you for joining us for this 19/7 webinar in the GIF Education and Training webinar series that is titled Overview and Updates of MSR Activities within GIF. I'll start with a few housekeeping slides. So on the next slide, first of all, if you have issues with sound, make sure that you've chosen the option Listen through your computer. If you have technical difficulties, we advise to look online for the Zoom webinar support page that you can see on the screen. And if you have a question, and I'll explain a bit more about that in a second, there will be a Q&A session at the end of this webinar, and you can ask your question through the Q&A pane. You will be able to share the recordings of this webinar that will be put on the GIF website shortly in the few days following the webinar. And you will receive a survey. If you have a moment after the webinar, please take the survey to help us improve this series. So on the next slide, you can see that to ask a question, and you can do that at any moment, and we will get to your questions at the end of the presentation. You can use the Q&A button that is at the bottom of your screen that will open a pop-up window where you can type your question and click the blue button to send it, and we will see it and answer them at the end. So on the next slide, so I'd like to introduce the moderator of today's webinar. Dr. Patricia Pavier is the National Technical Director of the Molten Salt Reactor Program for the US Department of Energy, the Office of Nuclear Energy. And she has been an active member of the GIF Education and Training Working Group since its inception. She was actually the first chair of this GIF group, and she is now the webinar lead for the Education and Training Working Group. She has been instrumental in establishing the present series of webinar, and she keeps it flourishing with the energy and enthusiasm she puts in it. So Dr. Pavier will facilitate this webinar and the follow-up Q&A session, and I now let her introduce our main speaker for today.
Good morning, good afternoon, good evening, everyone. Thank you very much for the kind introduction, Alexei. Always really appreciated. And it's, of course, my pleasure to have with us today Dr. Jerry Kreppel. He's a senior scientist in the Advanced Nuclear Systems Group of Laboratory for Scientific Computing at Paul Scherrer Institute Center for Scientific Computing, Theory, and Data in Switzerland. He earned his PhD in 2006 at the Czech Technical University in Prague, Helmholtz-Zentrum Dresden-Rossendorf in Germany, for his thesis entitled Dynamics of Molten Salt Reactors. Dr. Kreppel is the coordinator of the PSI MSR research at Paul Scherrer Institute, and is responsible for fuel cycle analysis and related safety parameters of Gen 4 reactors. He's also the chair of the Provisional System Steering Committee of the Gen 4 International Forum Molten Salt Reactor Project and co-developer of the IAEA MSR taxonomy. Dr. Kreppel has experience in the neutronics of liquid metal and gas-cooled fast reactors, and in neutronics and transient analysis of thermal and fast molten salt reactor. So molten salt reactor is a hot topic. Thank you very much, Jerry, again, for volunteering to give this webinar. And you have the floor. Thank you, Jerry.
Thank you very much, Patricia. It's a pleasure for me to give this third webinar from my side, this time on GIF MSR program. I divided the presentation into two parts. In the first part, I will speak generally about the GIF MSR role and position, about the molten salt reactor taxonomy development, about a brief history, which I would like to use for describing the concept development or evolution, and about MSR issues in a nutshell. In the second part, I would like to address the members and observers' activities in the GIF MSR project. So let me start with the GIF MSR project introduction. It is one of the 6 GIF reactors. It is similarly like for LWR organized only by Memorandum of Understanding. There are 7 signatories: Australia, Canada, Euratom, France, Russia, Switzerland, and the USA, and 3 observers: China, Japan, and Korea. This year, we are expecting to have new GIF framework agreement being signed, and it would require to sign a new MOU, and it is highly probable that Korea will join and become signatory. Historically, we have discussed already several times the option to sign an MSR system arrangement. So far, it from different reasons always failed, and it is a question nowadays in the new situations where the GIF platform as a for state and state-private cooperation may itself need redefinition how to organize it, because there are research organizations which are often financed from public money and required to publish openly. At the same time, there are private startups which prefer bilateral cooperation with commercial contracts. So GIF itself is looking a little bit for its position, and MSR probably may wait for the decision to sign the system arrangement. The activities of GIF, what the major one is, we have a biannual project meeting, typically held nowadays once online and once in person, but we are planning to switch back to both meetings in person. We are contributing to the GIF annual report, and together with the PRPP working group, we published recently the MSR PRPP white paper about proliferation resistance and physical protection. Together with the risk and safety working group, we are preparing on trying to finish the MSR white paper and system safety assessment. And we are also representing GIF MSR project at IEA technical meetings. We don't have any explicit interaction with NEA OECD, but as you may know, NEA acts as the Secretariat for Generation 4 International Forum. So it is also Secretariat for GIF MSR project. And at this place, I would like to use this occasion and mention that the Working Party on Scientific Issues of Reactor System prepared the FHR benchmark. So if you are interested, you can try to contact them. And the International Reactor Physics Experimental Evaluation Project included MSRE case in the Handbook of Critical Experiments. But back to GIF MSR project, we are interacting with IEA. The interaction is on the general level for whole GIF and IEA, where there is a regular interface meeting. There is also a GIF IEA cooperation matrix for all systems, inclusive MSR. And last but not least, IEA has several activities which should in long term aim at modification of the selected requirements and guides for non-water cooled reactors. So this work was intensified in 24 and will continue this year. And we are considering their cooperation of GIF MSR, risk and safety working groups, and IEA on these documents. But GIF MSR project members also implicitly cooperate on other IEA activities. So I put here a list of selected documents produced by IEA. And there is one outlier. This is the Status of Molten Salt Reactor Technology, published in 2023. And this is a quite sound document giving an overview. You can download if you wish. And this document includes the molten salt reactor taxonomy, which we have been developing at IEA. I was presenting this taxonomy in my previous webinar a little bit, but I would like still to go in details, this time focusing on the development of the taxonomy itself to justify a little bit which decision we did at that time. So let me now spend a few slides with that. So first step for that was the definition of MSR, and the definition was chosen so that the salt-cooled reactors were included in the taxonomy, because they have the salt has a prominent role in their core. The second step was having a look on MSR concepts from the past. So we tried to collect all the possible concepts you can imagine. And then we looked also to the more recent concepts. And as you can see, it is limited by year 2020. This is also based on the fact that the report was released around that time. And the third step was having a look if there is past taxonomy. And indeed, there is something you can call a taxonomy. It was a method of classification from 1978 from predecessor of PSI, Professor Taube and his team in the final report of their project tried to classify MSRs. And you can see here the list of classification parameters, and the number one there was the method of cooling, because it was time when molten salt reactor with direct cooling, where for instance, lead is passing through the core, directly being mixed with the salt and leaving the core again, was popular. So the second level was flux intensity or power. Third was the number of zone, and then firstly, number 5 is neutron spectrum, and kind of fissile nuclides and fuel cell type was also not belonging to top 3. So it was based really on the cooling methods and the number of zones. So for the IEA taxonomy, the first meeting took place in 2016, so quite some time ago. And there are many parameters you can consider, and there are thousands of options how you can organize such a taxonomy. And even the one we selected is not written in stone, so it can change easily in the future. But what we did as a first choice was that the taxonomy is limited to large reactors, because molten salt reactor provides such a designing freedom that you are to a certain extent limited only by heat exchange. And if you go to low powers where even the heat exchange is not limiting, then you can have really like thousands of designs. So the taxonomy was for large reactors, and the neutron spectrum was, even though it's tempting, was not selected as a highest rank criteria. And also the fuel cycle type or salt itself type was not selected. So finally, it was quite trivial. The number of materials, major materials in the reactor core was selected as the highest rank criteria. So you have a class with 1 material in the core, which is the fuel salt, with 2 materials, which is salt and graphite, and 3 materials, fuel salt, a barrier material, and then dedicated coolant or moderator. So molten salt reactors can be divided into homogeneous MSRs, where typically the chloride and fluoride fast reactors belongs, the graphite-based MSRs, so all MSRs where the graphite is used in the core, and heterogeneous MSRs. So those where there is a structural material separating fuel salt from either dedicated coolant or solid or liquid moderator. These 3 classes can be further subdivided. For the graphite-based MSRs, it is into fluoride salt cooled reactor, where the salt has only a cooling function and the fuel is embedded in triso particles in the graphite, and to graphite moderated MSRs, where the graphite acts as a moderator and the fuel is dissolved in the salt. Homogeneous MSRs can be divided into fluoride fast MSRs and chloride fast MSRs, and heterogeneous MSRs obviously into non-graphite moderated MSRs and heterogeneous chloride fast MSRs. In GIF MSR project, we adopted the IEA taxonomy, and here you can see the graphical form we use in the GIF annual report. and this a list of companies or concepts which are provided by the GIF MSR project partner. So it's not an exhaustive list. Some concepts may be missing, but it is what the partners provided. So this was kind of short, hopefully relatively short introduction of the decisions we did when creating the taxonomy. And now I would like a little bit to have a look on the history of MSR and comment a little bit there the evolution of ideas and concepts. So as you may know, it all started with aircraft nuclear propulsion program. It was the first big program dedicated to MSR, not only MSR, but quite intensively to MSR. And it was meant for aircraft propulsion. Therefore, fast reactors have been excluded. And it required high temperature, so water as a coolant was also excluded. So there were basically two options. One option was solid fuel cooled by liquid moderator at a high temperature, so let's say lithium or sodium hydroxide, or liquid fuel passing through solid moderator, so beryllium or beryllium oxide. It was relying on enriched uranium, and Oak Ridge, as the project main institution, had a look on many or practically all possible uranium compounds, and they were looking if they are useful for the reactor, and ended by uranium fluoride diluted in fluoride carrier salt. And the issues they have at that time are very similar with the issues we have now with engineering. It was minimizing of melting temperature for the salt, compatibility of the salt and other materials, and minimizing the core and shielding size and weight. So I will now go through the decays of evolution, starting with 1950s in the early time, let's say Oak Ridge MSR pioneering time, and there was ongoing military project, but in parallel there were also students looking on fast chloride and fluoride breeder. And they were probably faster in publishing because probably they have a deadlines and they wanted to be ready with their studies. So in 1952, two reports, one for chloride fast MSR and other for fluoride fast MSR were published. Already from the first report, it is obvious that chloride fast reactors have issue with neutron leakage, and you need to handle the leakage. So there was a reflector and blanket for that. For the fluoride fast breeder, what you can see is that it used graphite as reflector, and there was beryllium in the salt. So it was not really a fast reactor, and the breeding performance was so weak that this branch was kind of abandoned to a certain extent. In 1954, there was a report which included the ARE, the famous experiment with the beryllium oxide and salt. There was the fireball kind of conceptual idea how the aircraft propulsion could look like, but there was also like a heavy water moderated concepts, art concept variation. Later in the 50s, other two designs for chloride and fluoride fast reactors were published. They are a little bit more matured compared to the initial one, and especially for the fluoride fast reactor, you can see that the graphite reflector was abandoned, but still there was beryllium in the fuel salt. So still the spectrum was quite soft, and the breeding performance was not really breathtaking. In 60s, Oak Ridge was leaving the military constraints, so no more necessity for compact reactor. And there were two branches. It was thorium breeding cycle in moderated MSR and uranium-plutonium cycle in fast systems. So here you can already see quite a mixture of different concepts. In 1963, the first heterogeneous chloride fast reactor was proposed with the idea that if you separate the fuel from coolant, you don't need to extensively pump the fuel. 1965, the MSRE was constructed or started. At the same year, in the same year, there was a proposal of Mosul, which was lead cooled, directly cooled MSR with lead coolant from Oak Ridge, 1966. Quite similar design of lead cooled, directly cooled MSR came from UK. 1967, another homogeneous chloride fast reactor was proposed at INL. And in the same year, 1967, Professor Taube, at the time still in Poland, proposed a very, let's say, revolutionary or sporty system where the reactor was directly cooled by boiling aluminum trichloride. In the same year, in Oak Ridge, the two fluids MSBR version was proposed. And this was later abandoned because of the difficulty for the separation of the two fluids. In the 70s, on one hand, the MSBR project was kind of finishing or intensive. On the other hand, in 1973, it was stopped and the research was terminated. And the international research was kind of continuing with inertia, but however, later on, it was also declining. So what you can find here is the MSBR, molten salt breeder reactor. It is probably till now a concept which experienced the biggest effort so far. But there are also designs or experiments like the zero power frozen salt experiment from China. 1972, heterogeneous salt-cooled fast MSRs from Switzerland, from Professor Taube. Then there is another chloride fast breeder reactor proposal from UK. And 74, in the same year, something similar proposed by Professor Taube from Switzerland, and it was probably the first concept where uranium-plutonium cycle was used in the fissile zone and thorium-uranium cycle in the fertile zones, combination of both fuel cycles. And then there is another directly cooled MSR with lead. And in 75, probably one of the first waste burner, dedicated waste burner with driven zone from Switzerland. And in 1978, Dr. Otevit, a PhD student at the time, proposed the first chloride fast thorium breeder. He was actually a visiting scientist for a while in Switzerland with Professor Taube. So if you read his thesis and if you read a PSI report from the time, you can see some nice overlap since that time. So unfortunately, in the 80s, it was low interest period. LWR technology was dominating, and it seems that reserves of uraniums are sufficient. So those are like end of a kind design. So in 1980, the last design from Switzerland was a chloride fast reactor, which had a particularly liquid salt reflector. In Oak Ridge, they tried to propose the denaturated DMSR, denaturated MSR, with the idea that giving up the breeding, you can change the fuel cycle, you can denaturate it so that you avoid the proliferation risk, and you can make it so big that the graphite lifetime would be 30 years, so similar to the lifetime of the vessel. But it was also a kind of last of a kind of research was stopped in Oak Ridge after. 1983, the Russians proposed salt-cooled pebble bed reactor. And in the same year in France, there was probably last directly cooled MSR proposal. And the Japanese were holding the flag of graphite moderated MSRs in late 80s with the Fuji concept. Okay, in 90s, generally it was a dark period for nuclear energy. And it seems at the time that ADS, accelerated driven system, is the light at the end of the tunnel. So there were also subcritical molten salt reactors proposed. But generally, the accelerator is very useful if you want to burn minor actinides, and if your core is loaded only with minor actinides, you can have a problem with your Doppler coefficient, and you may need an external neutron source provided by the accelerator. But the molten salt reactors can probably compensate the weak Doppler through liquid fuel expansion coefficient, so they don't need this accelerator. And furthermore, ADS is good for a small dedicated burner, but it's not really scalable for energy production, because if you would scale it and ask big powers or many units, you would really need many of big accelerators. 2000s, it's start of generation 4. And this early time, the research was still driven by academic institutions and research centers. So I have here 5 concepts. It's the French Amster, graphite moderated either breeder or burner. In 2001, the Russians proposed the Mozart fluoride-based burner. 2003, from UC Berkeley, the salt-cooled reactor FHR. 2004, Rebus from EDF. It was rather outlier because other way it was fluoride salt time in early 2000s. And 2005, CNRS proposed the molten salt fast reactor. It became actually a reference concept for many European projects. So what I would like to illustrate here is the evolution of the concept, because probably all of the concepts which are nowadays being developed, they undergo such a devolution, but this is not public, so we don't know it, we don't see it, but for the MSFR, it is well documented how it was evolving. After 2010, it was time of private startups, and it's often I say it was one typical fuel cycle idea behind. I will not go in details in this list. It's the list from 2010 to 2015. Some of these startups are already discontinued. Some of them dramatically changed the concept. Some of them a little bit changed the concept. And this is from 2016 to 2020. Some of them are robust and have a lot of money and big effort. Some of them are just one publication. So as it is for us, for GIF MSR project, we are not really focusing or on selected concepts. We are rather, the implementing agents are typically state research center, national research centers, and we are all trying to support the startups in our country. So the list you can see here is based on the startups which kind of interfere or cooperate with us. So now I would like to open the third part of this presentation, speaking about MSR issues in a nutshell. So first of all, the basic features. For homogeneous MSRs, you use fluoride or chloride salt, which acts also as a coolant, and it's fast spectrum. And in case of chlorides, the spectrum is very hard, and it's very good for uranium-plutonium cycle, which can profit from hard spectrum. At the same time, it is transparent for neutrons, so it can be quite leaky, and you need to handle the leakage somehow. You need to have a big reactors or reflector or blanket. On the other hand, fluorides provide much softer spectrum, so it's much more suitable for thorium-uranium cycle, and it can be designed as a more compact system. What you need to do for these reactors, you probably need to replace regularly the vessel, because it is really irradiated. It's very near to the reactor core because it's forming the reactor core. For the graphite-based MSRs, exclusively fluoride salts are used because chlorides would have a high neutron capture. There is a possibility of closed thorium-uranium cycle, but it would be demanding actually. You will need fast fuel cleaning in that case. So typically a low enriched uranium fuel cycle is foreseen. And in case of solid fuel, trisoparticles embedded in the graphite matrix, you need moderating salts like lithium fluoride, barium difluoride, because only moderating salts provide negative coolant density effect. And you need to replace graphite regularly in these reactors. In heterogeneous MSRs, you have the separating material, and it's kind of eating neutrons, so parasitic neutron capture of that material. And the choice of this material will determine your neutronic performance, so bridging capability. And for fluoride salts are for the moderated systems because you don't want to use fluorides in thermal spectrum. And on the other hand, chloride salts are used in the systems with dedicated coolant because you need some reactivity excess for the dedicated coolant and the material of choice. Again, here you need regular replacement of the structural material. Now, all these reactors have in common one thing, and it is the reasonable temperature window for operation, because you have, on one hand, salt melting temperature, and on the other hand, structural material failure temperature or integrity. So you have typically eutectic mixtures of carrier salts and actinide salts so that you lower the melting temperature. So the molten salt reactor experiment, for instance, was operated with a salt where the melting temperature was 430 degrees. The MSBR salt with thorium had already melting temperature around 500 degrees C, so it's quite some step. MSFR is foreseen to operate in thorium uranium fuel cycle, and it has fast spectrum. So the beryllium was removed from the salt, and the melting temperature again increased by 60 degrees C to 560. If you would like to start this reactor just with plutonium, your melting temperature would be in the sky. Consider that the structural materials probably can be operated to 700, 750 degrees C. For chlorides, molten chloride fast reactor, it is back to 560 degrees C. And there is a salt, for instance, with thorium and plutonium, which is probably good for waste burning, which has again quite low temperature like we had at MSR time. In general, the solubility limits and actinized density are competing with melting temperature, and you need to find out, let's say, optimum or compromise between these, and also consider the structural materials you are using, and also safety features and so on. Similarly, like with temperature window, there is a redox potential window, and there is also kind of trade-off of salt stability and structural materials corrosion. So the salt itself is ionic liquid and can be irradiated for infinite time. And no matter of the fuel cycle type, it is always good to keep the actinides as long as possible in the reactor. So what you want to remove is actually the fission products, but they don't want to be removed. They are typically the last one to leave. And you need to control the salt. You need to control the redox. You need to remove impurities so that you are in the kind of safe redox potential window. So if you would be on the oxidatory part, you see that you can the corrosion or oxidation of the structural material can be quite strong. If you will be on the reductive part, you may have an issue of precipitation of actinides and other elements. So according to your system, according to your structural material, according to the salt and fuel cycle you select, you need to find out your redox potential window for operation. If you would then control this redox, and if you would keep the salt clean, not necessarily there are big issues with corrosion. So there is temperature window, there is redox potential window, but you should also consider the fuel cycle type and combine them all together because they should kind of fit. So from that perspective, the salt has 5 components, and it is typically only the last 5th component, the fission products, which you need to remove. And for that, you can use several different methods. Sometimes you need to use several different methods to get to the fission products and to remove them. And you can apply these methods in many different modes. So all together, it provides many different variations. Now, all what I said so far is leading to something which is needed, and it's a kind of database of salt parameters. So we have thermophysical and thermodynamic parameters, and here I illustrated with thermodynamic databases. There are 2 most sounded is the GRC MSD database, The development started in 2002, so more or less with the first European MSR project, and is being developed by JRC. And the MSTDB database of USA developed since 2021 in collaboration of Oak Ridge, University of South Carolina, NIMS, and Molten Salt Reactor program. So those are very important databases which we need for the salt properties, and which to a certain extent influence the MSR reactor designing. The last slide of this part, I wanted to speak a little bit about the safety and licensing on very high level. And I would like to express rather personal perspective here, that nowadays the light water reactors are based, the core of light water reactors is based of assemblies and pins. And the core does three major functions. It is the location of first confinement barrier, it is the location of primary heat exchange, and it is also shaping the neutron flux area. So in case of core damage, you are losing these three functions, and it is considered a severe accident. It's a safety threat, it is irreversible, and it means facility loss. If you look on MSR, in some MSRs, the core is shaped by solid moderator or just by vessel. So, and the liquid fuel relocation from the core does not always mean severe accident. And core damage has thus completely different importance in MSR. And unfortunately, if you look on the regulations, they are not necessarily prepared for MSR. So therefore, there are activities around the globe. Let's name in particular the NRC activity for that. And the IEA is also trying to do that, but MSR is really tough in that sense. In the past, I was also showing these figures illustrating the barriers, but I would not go to detail here. I would just mention that even though traditionally we speak about three barriers, when you do the probability safety assessment, you don't do it for three barriers. You have probability safety assessment for core damage frequency, and then the next one is for the barrier, for the containment failure. So you do only two of them. So let's see if you will need two for MSR or if you will make only one, but not necessarily the three barriers or the first two barriers for LWR are fully independent. Okay, this was the first half, the introductory part, and now I would like to switch to presenting the activities of GIF MSR partners. So as I said, we have 7 signatories and 3 observers. Let me start with Australia. So there are 4 areas of interest in Australia. On one hand, they are looking on radiation damage of structural nickel alloys. On the other hand, they are studying the high temperature creep and molten salt corrosion of structural alloys. They also do develop a synrock type waveforms for fluoride salt immobilization. They do cooperate with several startups on with that, and testing and multi-clay modeling of graphite and carbon-carbon composites. If I switch now to Canada, the landscape of Canada has 3 major streams. The first stream are the big energetic reactors in operation. The second stream are advanced reactors, where in particular you can see Moltex and Terrestrial Energy MSR companies. And in the second stream, there are off-grid micro reactors with small power. I'm not sure that there is MSR. In my personal opinion, MSR is not really good for micro reactors because the salt needs some controls and redox control and so on, and off-gas handling and so on. So not necessarily MSR is the best for micro reactors. I would rather go for bigger reactors. If I go to the actual work or topics addressed in Canada, for the fuel and coolant salt properties, they are performing some DSC measurements. They do some molecular dynamic studies and measure thermophysical properties of selected molten salts. From material and components, corrosion experiments of the SS316. developing of reference electrodes, and exploring methods for redox potential control, and investigating impact of fission products on the redox potential. Now, since Moltex is kind of active in Canada, I would like to show a slide of Moltex company here. Say 2 sentences, 2-3 sentences about the concept itself. So it's a stable salt reactor. So it's a heterogeneous MSR where the salt is not circulating, is being sealed in the bins, and there is dedicated coolant. I'm not sure if it is also chloride salt, but it is profiting from the advantage that you don't need to pump the fuel salt. The fuel is liquid MSR, so it's salt. At the same time, it's sealed, so it has some issues like solid fuel reactors. So you have assemblies, you may need to reshuffle these assemblies and care about power peaking more than in solid fuel reactors. The next GIF MSR project partner is Euratom. And traditionally, Euratom is financing molten salt reactor projects since 2001. And there is nearly uninterrupted series of these projects. At the end of 2023, the Samosafer project finished. Mimosa was launched in parallel for kind of multi-recycling of spent nuclear fuel in molten salt. And Endurance, like the continuation of the series of the project, was launched in fall last year. And yeah, I think all major European partners are involved, and inclusive the startups. Speaking about the startups or companies, I can name 4 for Euratom if I am excluding France. It's 2 Dutch startups, Copenhagen Atomics and Seaboard Technologies. One with the idea to have a small reactor in the transport container. Second with the idea to have a power barge, to have a reactor on a barge. Dual fluid reactor used to be MSR startup, was using actinides chlorides without any carrier salt as a fuel. You can imagine the melting temperature was very high, but they recently switched from salt to liquid metal fuel alloy. And Horizon, with an idea that the core can be composed from quite large fuel cartridges. I will come to it later. So Euratom as such is directly financing the joint research centers, and especially JRC Karlsruhe is a competence center for MSR and fuel properties. So they can do everything you can imagine, from synthesis, thermophysical properties measurement, irradiation, reactor safety, up to the thermodynamic database I already mentioned. If I go to the highlights, Euratom organized last year a workshop dedicated to standardization, so putting science into standards for MSR. And then there are several highlights from JRC and their involvement in European projects, Samosafer and Mimosa, and also like participation on a high-level IAENA meeting, and yeah, as I already said several times, extension of a JRC thermodynamic database in collaboration with partners. But Euratom is also represented by individual countries, so I have a very swift kind of presentation of the activities, starting with Czechia. So CV Řeš, nearby Prague, they were measuring neutronic properties of lithium fluoride, barium difluoride in their LR0 reactor. Nowadays, in the frame of Mimosa project, they are looking on fluorides, and they are also participating in Endurance. In the Netherlands, NRG, here I would name the Saga 2 and Saga 3 experiment with gamma irradiation of the granulated salt. They also did Salient experiments, and the Salient 3 is scheduled for summer of this year. In Netherlands is also TU Delft. Here you can see the list of theses, so you can see the extent of the effort. I will not go to the detail. And then I would also explicitly name Italy, especially Polymé, where Stefano Lorenzi from Polymé is the project coordinator of the endurance. And they are historically good in modeling and thermohydraulics of molten salt reactors. They had also the Dynasty facility. And then also, for instance, Denmark with DTU, which is collaborating with Seaborg and JRC. Yes. With that, I would switch to the Euratom, let's call it Euratom startups or companies. So first one is Copenhagen Atomics with their onion core. They are challenging the taxonomy to a certain extent because it is obviously heterogeneous moderated MSR, but if you scale a little bit the zones, you can discuss if this is heterogeneous or 3 zones homogeneous. But once again, this is the issue of the size. So with 100 megawatt thermal, you are on the edge of being small. And you can see also the scalability. So they don't want to increase the size of the reactor. They plan to operate many of these reactors side by side. And their advantage is really that this is probably one of the most compact thorium breeder, but it is determined by the separating material. So firstly, you need to qualify low neutron absorption separation material to achieve that. Another startup is Seaborg Technologies with their power barge, and they are from very beginning pursuing this idea that you put reactor on a barge and you can fabricate it on a given spot and transport it where it is needed. It is based on the graphite moderated MSBR type, but they don't plan to breed, so they don't need to have lithium beryllium with enriched lithium salts. So the foreseen initial enrichment is approximately 2% of enrichment for uranium. The third startup is Horizon. Horizon is also challenging the taxonomy from certain perspective because the core is composed from cartridges, but individual cartridge is quite large, and individual cartridge can be considered as homogeneous fast reactor. But together, these cartridges are forming heterogeneous core. Yeah, but it is really interesting from classification perspective. Okay, let me switch to France. The landscape in France is formed mainly by the project France Relaunch, where there was ISAC financed as first in 2022, looking at transportation of actinides in MSR, followed by MSR waste, looking on the waste forms, such as transmuter, and Portos, dedicated to synthesis of thorium tetrachloride and purification of the salt. France is also heavily involved in the European project, so Samosafer, Mimosa, and Endurance. And there are French startups, Narea, which is fast chloride micro MSR using actinides, and Stellaria, which is small to big MSR, relying on homogeneous chloride fast reactor. The major player is CEA as a national research center, and they do the similar activities like national research centers in US, for instance. So it's a code development and simulations in all different fields. There are design activities, let's explicitly name here the Aramis concept. They are also involved in the national and European project. And they also do chemistry from synthesis, corrosion, material properties. And they are supporting French startups through the France 2030 call. In particular, I would name here the ISAC project with the design and simulation activities for the Aramis concept. And as you can see, there is a list, quite long list of PhDs which are either ongoing or recently finished in several different locations. So speaking about French startup, there is NARA, as I already mentioned. It's a micro reactor, fluoride fast reactor, chloride fuel, probably chloride coolant, but they also admit fluorides in this slide. Low power and yeah, probably dedicated to waste burning because the core is small for breeding. Stellaria, it's homogeneous chloride fast MSRs, so the size probably may allow breeding. I'm not sure about breed and burn, but yeah, if they are really good in utilizing the neutron leakage, probably it's possible. What is really special here is that they don't use pumps. They are relying on natural circulation. Yeah, and that's it for France. The next country in the list is Russia. And they are developing the Mozart burner since 2001, so quite some time. And what you can see now, they are proceeding, and Rosatom as a vendor is preparing. Yeah, I don't know if this reactor has a name, but probably yeah, it's kind of test or demonstration reactor on the Mozart way. And Kurchatov is the scientific leader, and there are many other institutions which are involved in this project. If I go to the highlights, you can see something similar as for the others. So it's looking on the salt properties, measuring properties, looking on the impact of fission products, compatibility of the materials with the salt, and yeah, okay. Also, welding is listed here, and thermal property measurements. Okay, I have Switzerland now in the list. Switzerland is a dwarf. I mean, we are here in Switzerland, we are relying more or less on students in our MSR project, and the major function is education and monitoring. There is no really strong MSR system preference. We are focusing on safety and sustainability. And as a highlight, what I would name here is, of course, the participation. We are participating in Endurance as a third country with substantial contribution, I would say. And PSI and Copenhagen Atomic signed a large-scale experiment collaboration agreement. So I think the major milestone ahead is trying to license it. And then we can proceed. I'm not sure about 2026. 2027 would be also great. Let's see how it will go, but it's exciting, I must say. Okay, there is also, of course, USA, and maybe you have already seen this advanced reactor timeline, but as you can see, MSR is featured prominently there. There is this test reactor, Natura, at Abilene Christian University. There is Kairos, there is Southern company, and TerraPower with AMCRE, Hermes 2, and also IMSR from terrestrial energy. If I should go in details in the USA landscape, the Department of Energy, especially the Office of Nuclear Energy, they remain focused on enabling MSR industry and building the supporting infrastructure. And the largest fraction goes through the Advanced Reactor Demonstration Program, RDP. So DOE NE continues to support MSR via MSR Technical Campaign, Advanced Fuel Campaign, Nuclear Energy Advanced Modeling and Simulation, NEAMS, Nuclear Energy and University Program, NUP, and through the Gateway for Accelerated Innovation in Nuclear, so GAIN vouchers. There is also activity in a regulatory commission developing technology-neutral, performance-based, risk-informed regulatory framework. Looking in details in the MSR landscape, the MSR campaign is covering more or less all the field you would expect. So it's the salt chemistry from thermophysical, thermochemical properties, experimental and theoretical. It's technology development focusing on off-gas management, radionuclide release, and monitoring and sensors. Includes modeling and simulation, but also irradiation, advanced material testing, surveillance technology, interaction between graphite and salt, and structural materials and salt, and also looking on the separation of radioisotopes, which may be of interest for the MSR community. One of the highlights is the development of the database, and that many companies are pursuing the development in early 20s and early 30s. Sorry. Modeling and simulation is for electrochemistry to material science assumptions to decrease the technical difficulty of implementing MSRs. So it seems that there is really like now a pressing need for safe and reliable energy production, and it's driving MSR. But none of the companies has yet reached the market. So saying that, I can say that there are some big milestone achieved already. So for instance, for Kairos Power, let's say that they break ground on the salt production facility to produce high purity molten salts, coolants, in October 24. And also in October 24, they signed an agreement with Google, and it was medially well covered, and it raised, I would say, big wave of interest of also of general public for that. Another example is the collaboration with TerraPower and Sounder Company, where there was this integral energy test with more than 250 documented lessons learned. And nowadays they are developing this molten chloride reactor experiment M3, which should hopefully operate soon. And another prominent example is the activity at Abilene Christian University. So they already finished the construction of the building, and Natural Resources received construction permit for the MSR1 at Abilene Christian University in September last year. So let's see how fast there will be. There is also one highlight related to terrestrial energy, because this company redomiciled to USA, and on the picture you can see the layout of the dual IMSR facility. The idea of this company is quite simple. It's to take the graphite moderated MSR as it was developed in Oak Ridge and try to do as fast as possible the minor modifications to it and put it on the market. As trivial it may sound, it is still quite complicated, but crossing fingers for that. And then from US, there are also newer startups, both dedicated to waste burning. It's Curio and Visor. I don't have more information about that, but it seems like chloride fast burners. Okay, now the few last slides I have are dedicated to the observers. So China, as a prominent observer of GIF MSR project, has a long-term project of TMSR of the sign-up in Shanghai, and they have two branches of this project. Is a branch with solid fuel, TMSR SF, and branch with liquid fuel, TMSR LF. And in the branch of liquid fuel, they were since many years planning a test reactor. And I have the honor to announce that this experiment or this test reactor is not only in operation, but was already operated for quite few days on full power. So if I start from the beginning, the building started in 2018, and in fall 2023, the criticality was reached. In June 2024, they reached to full design power of 2 megawatts. And in October last year, they operated the reactor for 10 days with thorium fuel, and they could detect protactinium-233. That's very great news. The other observer is Korea. And Korea under the new framework may become signatory, so become a member of this project. So we are really looking forward for that. And in 2024, Strategic Alliance for Promoting Public-Private Cooperation was formed, signing an MOU, and Hyundai Engineering and Construction was selected as a head for concept design and managing and coordinations. From scientific highlights, of course, the usual suspected. So you have fuel coolant salt properties. So this preparation of the salt, determining the phase transition, completion of the design, fabrication, and commissioning of molten salt loops, and experiments with off-gas unit process, corrosion rate evaluation of candidate alloys, and from reactor physics, of course, some neutronic calculations for designing, and coupling of Monte Carlo and CFD codes for MSR, which is in progress. Okay, is all from my side. I'm open for your questions, but before, I guess Patricia would like to announce the next upcoming webinars. Am I right?
It's gonna be Alexei, but thank you so much.
Yes. Thank you so much for this very dense and fascinating presentation. Yes, please, thank you all for joining. Don't leave, of course, we'll have the Q&A session in a moment, but please register and share the information about the upcoming 3 GIF education and training webinars. The next one is end of February. That will be an overview and update of activities in the very high temperature reactors field within GIF. The second one will be end of March, 27th of March, and we will have Marta Gospodarczyk from the IAEA that will present about the nuclear power, electricity, and beyond the grid, and the data-driven insights from the IAEA's Power Reactor Information System. And mid-April, on the 15th of April, we will have a presentation on advanced manufacturing in support of Generation 4 reactor systems. So please register for those webinars. The 2 first ones are already on the GIF public website, and you can register, and the last one should be next week. And on the next slide, also, I would like, that's very important information for PhD students and young researchers. The Generation 4 International Forum organizes the 3rd edition of the Pitch Your Generation 4 Research Competition. The applications for the first phase are open until the end of February. So if you want to present what you're currently doing, researching on Generation 4 related topics, please apply. The first phase, you need to send us an executive summary of your research, and then pre-selected candidates will be invited to present in a short video pitch their research. It's a great opportunity to gain visibility, and the winners will be invited to present in webinars of the same format as the one you're watching now. So please join us, spread the word about this competition if you have people in your network that could be interested. Yes, so thank you, and I'll leave the floor to Patricia to moderate the Q&A session.
Yeah, thank you very much, Alexei. And I would like to add for the Pitch Your Gen 4 Research Competition, the first and second winner will have the opportunity to participate in a GIF event. So that could be either the expert group, policy group meeting, or also a GIF forum that we have every 3 or 4 years. So stay tuned. We love to have you on board. I think it's very exciting. For the audience, if you know PhD student, postdoctoral fellow, junior scientists, engineers, please send them these slides. I see the first question is, are the slides going to be available? Yes, they are. All our webinars, so 97 webinars, have been recorded, are archived on the GIF portal, as well as the PDF file. So yes, everything is available. Feel free to pass on the information. This is a very good source for people who wants to know more about advanced reactor system or cross-cutting subject. So, Jiri, are you ready?
Yes.
We have a few questions. So the first one, is it possible to use MOX fuel in a reactor with molten salt coolant?
I think it was also by chance in Switzerland in the past that they had a look on it. I'm not sure if the reports are in German or English, but you can theoretically find it. They were looking on salt-cooled fast reactor. So you simply, instead of lead or sodium, you consider to cool it with salt. Since many startups are considering relatively standard steels like SS316 or others, so probably it would be possible. Yeah,
Okay.
I cannot name now a killer which make it not suitable. But of course, it would bring some advantages because it's not so heavy like lead, and it has also high boiling point as a lead. Yeah, so
Okay,
try.
and and there's a second part in that question. What kind of cladding structure should be compatible with other materials?
Yeah, so once again, I would say if you really control the redox potential, and especially if you have coolant, which is not evolving much, so you can control the redox potential, then probably you can rely on standard steels. But in recent years, nobody did this kind of study, so I cannot tell you. I don't remember if there was a killing point for that. But yes, somebody had already this idea, and I don't remember why it should not work. So, yeah.
Okay.
Sorry.
Thank you. No, thank you very much, Jerry. What are the constraints in using software fact stage demo version for molten salt?
Okay, I'm not really a chemist, an expert in that, but if you use tools like this, you always need to have the database. So you should be capable to use the code, first of all, and second of all, you should have access to the database. So I would say the constraints are based on the database. So you should find out your access to the database. So you can look back on my slides and try to contact one of these developers and discuss with them how to access the databases.
Yes, and we have in the States the database at Oak Ridge National Lab. So if you want to send me an email, I can put you in contact with those people. Another question, are structural materials for MSR, like for example stainless steel, qualified for use in nuclear reactor? And if not, how do you deal with this issue?
It's a very good question, because you may know from literature that in the Oak Ridge time during MSRE, they were using high nickel alloys, so-called Hastelloy, and they found some issues of tellurium cracking and so on. So they provided kind of modified Hastelloy, and this material is not yet qualified in ASME code. So even if you would like, then probably you cannot use at the moment. So you need to rely on materials which are already there, some high nickel alloys which are there, or stainless steel. So putting a material there probably would be not so straightforward, but I think there are some activities ongoing. And if you pick up a material which is already there, once again, people may often say there is an issue with corrosion, but if you keep your salt clean from impurities, and if you control the redox potential, then the corrosion is not so terrible, and you can rely on existing materials.
Thank you very much, Julie. Yes, I just add the 6 code qualified materials for nuclear applications, but there's a lot of research around the world on advanced materials. The next one, isn't the molten salt components of what TerraPower are doing more for storage than actual fission in the molten salt?
Yeah, that's a beautiful question. So yes and no. TerraPower is actually following two concepts. One concept is a breathe and burn sodium fast reactor. And for that reactor, they are considering the heat storage in salt. But in parallel to that, they are also following the path of a breathe and burn in chloride fast MSR. So yes, they are using salt in both of these ways. So salt as a heat storage for sodium fast reactor and salt as a fuel for breathe and burn MSR.
Thank you very much. The next one. Also, why isn't that dual fluid design categorized as MSR?
Yeah, actually, they changed the fuel from molten salts to molten metallic alloys. So from that perspective, they are out of Gen 4 because metallic alloys are not really covered by Gen 4. So if you should add them to Gen 4 somehow, somewhere, probably you would add them to MSR because it's quite revolutionary and it has some common features with MSR. Yeah, but it's the change of fuel, which if you don't use salt, by IEA definition, if there is no salt in your core, you are not MSR.
Mm. Thank you, Jiri. Another question about radiation chemistry. So the person is asking about radiation chemistry. The Brookhaven National Laboratory is doing radiation chemistry for molten salt. In Europe, there is nothing to his best knowledge. You mentioned that carrying salt could be irradiated without damage, but there is no dedicated studies that have been done. It seems the statement is taken for granted by the community. Water reactors won't work without understanding the radiation chemistry of water. Thus, my question is, how the radiation chemistry community fall from the development path?
Mm-hmm. I see. Yeah, I must admit that I'm not a chemist again, so it's outside of my competence. I can only rely on memorizing some discussions during the project. And from the report I read, but once again, it's ionic liquid. And you are fissioning atoms in the liquid, so you are ionizing it quite strongly. You are producing fission products which are also strongly ionized, and so on. So it's very harsh environment. And yeah, there were at least two reactors in operation, at least MSRE for quite some time. So it really seems that the carrier salt is recombining. So you have kind of dynamic equilibrium, and it seems that it's not problematic. But you are also fully right that we should study this, and you may be right that there is nothing around in Europe if you say it as an expert. But I cannot say much more about it.
Mm-hmm. And I can say something. It's all about funding. If you get a lot of funding, then you can definitely look at radiation chemistry. But most of the time, we don't have enough funding. So I encourage all the surgeons to continue talking about molten salt reactor to get more funding over the world to study these kind of topics. Next question. What are your thoughts on the use of AI in the nuclear industry?
Oh, yeah, I must admit here that I'm rather supporting the natural intelligence than AI. Of course, it can be applied in several fields. I'm not sure that you should apply it in core designing. And if you would apply it, let's say, in kind of concept brainstorming, that probably you should be careful to ask the right question, because as good will be the question, so good will be probably the answer. But if you will have a good question, probably you will not need AI to answer it. So yeah, it can be good for multi-optimizations. It can be good for developing kind of surrogate models and so on. It can simplify our life. So it has definitely a place there, but yeah, I would personally say it is not a holy grail. Natural intelligence is also important.
Thank you, Jerry. Is there any relationship? I'm sorry, the question are moving. So is there any relationship between chlorine 37 enrichment with HALEU enrichment? Highest LO enriched uranium.
Yeah, so basically, if you enriched the chlorine, you remove the chlorine 35. Based on the cross sections we know nowadays, you reduce the parasitic neutron capture on chlorine. If you reduce parasitic neutron capture on chlorine, you have more neutrons for other captures, so probably it allows you to reduce the uranium-5 enrichment, so that you have more neutrons which can be probably captured on uranium-238, creating plutonium-239, and so on. So yes, it is interconnected. The better your neutron balance, the lower the enrichment.
Oh, thank you. Always learning with you. Thank you so much, Jerry. After a Samosafer project, is there any plan to commission MSFR soon?
I'm not sure that MSFR is foreseen as a concept which is really planned to be constructed. I would say that rather it will be so that the French will design other system which will be inspired by MSFR. As I name it, the problem is always, to a certain extent, the temperature window. So it is really interesting to breed in thorium cycle, but the temperature window is getting smaller with that. And if you really want to breed in thorium cycle, you need to start the cycle, and that's another issue. So inevitably, you will need to start with something more grounded, like enriched uranium. And even with enriched uranium, it does not need to be so straightforward. So yes, I would rather say that MSFR is kind of reference academic concept, but should it become industrially serious, then it will be overtaken from the university to some engineering company, and it will become something like Aramis, but probably not MSFR.
Okay, thank you, Jerry. Someone said, thank you for your answer. Many thanks. Another question, can you come back to the size of reactors and why you mentioned micro-reactor might not be a good option for power generation purpose? What are the actions being currently taken to prepare regulators for MSR licensing? So that's two questions. One about micro-reactor and then the MSR licensing.
So once again, it's my private opinion, yes. But look, you have molten salt reactor. You need somehow to care about the gaseous fission products. You need somehow to care about the redox potential and so on and so on. So based on that, I'm not really convinced that MSR is really good for microreactor, because I don't imagine that you will have microreactor with an army of chemists staying around. So maybe you can do microreactors with salt when the salt will be sealed. But from operating perspective, having a kind of open off gas system, micro MSR, may not make economical sense. So the remote operation may be not so straightforward, but it's my opinion. I don't see any other issues with that. Yeah.
Yeah. Okay, thank you. And for the licensing, are you aware of any step taken to prepare regulators for MSR licensing?
So first of all, the regulators are already aware that something like this is coming to them, and typically NRC in US is very active. The Canadian regulator is active. some regulators cooperate. So there is agreement between France and Canada and USA on that. IAEA is trying something, but IAEA is probably not including MSR in the first modifications. So typical, the first action is that the regulator is learning about the technology. So that they ask experts for a seminar or a course to understand the technology and the differences. And yeah, probably you can say more, Patricia, to help me to answer this question.
Yeah, no, yeah, we in the US, I'm not going to talk for other countries, but in the US, we have taken steps, and David Olcombaiso is on the call also. We have started probably in 2015, 2017 timeframe to give classes also to educate the NRC. There's a memorandum of understanding between DOE and the NRC. We have meetings. NRC is getting better and better. They have constant meeting with different developers. It's all about education, training, understanding concepts, talking with the NRC, and you saw some of the concepts have been already authorized with the construction permit. So in the States, I think NRC is really engaged, and I believe in other countries it is the same. Another question: are any of these reactors? It's about proliferation. Where is that? Voilà. Are any of these reactors susceptible to weapons proliferation?
So I would answer in two different kind of perspectives. The first one is, if you are a country without a bomb and you should care about proliferation, or you should not care if you would like to have a bomb. There are two all good ways. One is enriching uranium, and the second one is irradiation of low enriched uranium in any reactor and separating it with well-established Purex method. So those are the two ways you do bomb. Not looking on the fact that nowadays a majority of the bomb around the globe are thermonuclear. So imagine that you are a state, you would like to have a bomb, and you would firstly build MSR. No, this doesn't make sense. Okay, to be more serious, of course, proliferation is an issue, and we speak here about safeguarding. We speak here about controlling a state, that they will not do something wrong. So safeguarding for liquid fuel is a little bit more tough. You don't have numbered assemblies. So you will need to have something maybe like a hot chamber, which should be sealed. And whenever you open it, then IAEA inspectors may be around, or you can as a designer, you can propose. Actually, it is on the designer to propose way how to control the materials balance. But once again, if you would like to have a bomb, MSR is not really easy step to go.
Yes, and I can add something also. We are encouraged, especially in the States, to look at a safeguard by design. There's a program which is called the Advanced Reactor Safeguards that is led by Ben CPT. He did a webinar, a GIF webinar. So we are really emphasizing a lot on safeguards by design. Another question on the fuel cycle of MSR for you, Jerry. All the time I'm thinking we are at the end, and no. So thank you very much for your time and for answering to those questions. So regarding the fuel cycle for MSR, which are the initiatives or guidelines that are being developed to access the high variability of fuel and coolant requirements? Is there any database or a report about that? Do you consider the high amount of MSR design is a risk for the nuclear fuel cycle for their deployment?
Okay, it's a quite complex question. I would say we did analyze fuel cycle of many different MSRs here at PSI. So you can have a look, for instance, on a PhD thesis of Boris Homburger. What I would say is that there is not really a clear winner. If you take this taxonomy, if you take the 6 basic families, there is not clear winner. There is always pro and contra. There is nothing like perfect given to us by nature. So yes, you should know what you want to achieve with your MSR and how to profit from the flexibility. From another perspective, it is always about compromises, and you need to choose your salt, and the salt should really follow the requirements for temperature window, redox window, for your fuel cycle type, and so on and so on. You should be aware what is your final fuel cycle, what is your initial fuel cycle, what will be the transition, and so on, and design it accordingly. And the reprocessing itself, maybe the key point, actually, in my personal opinion, if we manage a breakthrough in the reprocessing, so if we find out kind of a robust, safe, and simple method how to separate fission products from the salt, then probably MSR will be really the technology for the future, because it will simplify everything. Yes, but nowadays, since the fission products are typically the last component, you need to have a complex reprocessing. The question is, would you do it in situ or ex situ, and so on and so on. Yeah, this multi-parametric optimization, and historically in the 10, 15 years ago, typically it was focusing on the neutronics, the neutronic performance. But nowadays we are getting more to the ground, and we are thinking how to put it in operation. So forgetting about thorium and focusing on enriched uranium and so on. And to the last part of your question, I don't think that the high amount of designs is a risk. During the first pioneering time of nuclear energy, in the 50s, let's say, there were also many different designs and companies and so on. And sooner or later, there was a crystallization, and many of these companies disappeared. And later on, there were 2, 3 robust winners. So I think something similar will happen with MSR. We don't need to regulate other way than waiting for natural selection.
Okay. Thank you very much, Jerry. There's a question about waste, and I know you're not a waste specialist, so yeah. I'm going to let the audience know that we have a GIF webinar that was proposed in June 2023 by Brian Riley, John Vienna from Pacific Northwest National Laboratory. So I am inviting you to listen to their webinar. It was specifically done on waste for molten salt reactors. So June 2023, you go to the GIF portal, you will find this webinar on MSR and waste. The next question, Jiri, why are Thorizon, Neira categorized as heterogeneous MSR while Stellaria is homogeneous? The 3 of them are using similar salts, I believe.
So let's start with the definition. So homogeneous MSRs, they have only salt in the core. And if you look on Stellaria, they have kind of natural circulation, so there is some structural materials leading the flow, but in the core there is only salt. There is nothing else. There is no moderator. There is no other fluid. So far for Stellaria. Thorizon use something very similar. So you have a cartridge where the pump is pushing the salt to the top of the cartridge, and it is nearly a homogeneous fast MSR. Nonetheless, each individual cartridge is subcritical. So to make it a active reactor core, you need several of these cartridges. And the core itself is thus composed from the salt, from the wall of the cartridge, from, I don't know, some gas in between, and so on. So yes, it is really a system on the edge, because it's a set of homogeneous reactors which together may be heterogeneous. And Neira NAREA is, I would compare it a little bit to Copenhagen Atomics. It's a container, transport container reactor, quite small reactor, and there is structural material in the core separating fuel from coolant. So the big difference to Stellaria is that there is dedicated coolant without fuel, just coolant salt, which is passing through the reactor, cooling the reactor, and the salt does not need to be pumped intensively because of that. Whereas in Stellaria, you are pumping the fuel salt itself to transport the heat. So this is the major difference.
Okay. Thank you, Jiri. We have 3 more questions and then we're done. I see it's 7 o'clock in the morning for me. So next question, could you clarify or mention what are the major reasons that makes MSR more competent than pebble bed reactor?
Okay. Are you sure you want to hear it? Okay. So first of all, I really like closed fuel cycle. No matter if you want to burn the waste in closed fuel cycle, no matter if you want to breathe in uranium thorium cycle or plutonium, uranium plutonium or thorium uranium cycle. But the beauty is the closed fuel cycle. So let's call it circular economy of actinides. Yes. So HDR relies on triso particles embedded in graphite matrix. If you don't process it, the waste is volumetric. It's more volumetric than for LWR. Processing is not so straightforward, but even if you do process it, HDR cannot breathe. It is clear that it cannot breathe in plutonium cycle, but even in thorium cycle, it is on the edge of breathing, and it is slightly below the edge, so it cannot breathe. It is hard to reprocess, and it is probably therefore hard to close the fuel cycle. So for me, that's the major reason why MSR it's more generation 4 system than HDR.
Okay, thank you. Are any of the mentioned MSR designs disputed whether they are actually Gen 4 or not?
Okay, so we nearly addressed the question in with the previous one. So you should firstly define what are the requirements for generation 4 systems, and they are related to economics, proliferation, safety, and fuel cycle. And I would say we are now speaking about concepts. Sometimes it is even pre-conceptual designs. So I would say it's too early for that. Once we converge to something more robust, we can speak about it. But generally, there is a potential. In my opinion, there is a potential that second or third generation of molten salt reactors will be really economic, will be really inherently safe. I mean, we have light water reactors. They are safe, but the safety is engineered, so to say. So we have a dangerous source term, and we are just caring not to release this source term. We can organize MSR so that the core is kind of more inherently stable, and there are smaller driving forces which wants to disperse this source term. So in long term, I see potential for MSR to be really safer and cheaper. And once again, we need for that, for the sustainability and economical part, some fancy reprocessing method which will simplify the fission products removal. But to say which one is more and which one is less, if you have a dedicated burner, I don't know, is it MSR? Is it Gen 4 system or not? Yeah, I would say, yeah. I would not like to speculate, but there are 6 selected Gen 4 system, and I'm not sure that all of them fulfill the Gen 4 criteria.
Okay, thank you, Jiri. Last question. What type of fuel cycle risks do you see regarding the enormous amount of MSR designs?
Oh, I'm not really sure to grab the idea of the question. So risk related to fuel cycle and the amount of designs. So you can design MSR badly. There are options how to design MSR badly. You can do heterogeneous MSR with 2 fluids, having positive coolant density effect. You can have a graphite moderated MSR with also positive coolant density effect or graphite temperature feedback. So there are options how to design MSR badly, but probably nobody will proceed with these options. I'm sure that they will be kind of discontinued, these bad options. So not sure how it is this related to the fuel cycle. Fuel cycle risk. Yeah. So I would say the probably the opposite. Once we find out reprocessing technology which is easy and straightforward, the designs will be augmented accordingly. Yes. So if nowadays there is somebody, and a few years ago many concepts were claiming, okay, my reactor is thorium breeder, and the same companies are nowadays saying, okay, we will start with 5% enriched uranium, because thorium recycling and thorium cycle starting is not so straightforward. But I don't see it as a risk.
Okay. Thank you very much, Jerry, for all the questions. We had a total of 20 questions. You answered to each one of them. Thank you very much. We still have 80 participants, and we passed the time. So I'm sorry it was a bit longer, but I think it was really worth it to listen to you as an expert in molten salt reactor. Thank you very much. Everyone. Alexei is still there. So thank you, Alexei, for organizing the webinar and being behind the scene with the Zoom. Thank you, everyone. We give you again a rendezvous on the 19th of February for a VHTR within GIF, which will be our concluding a series on updating everyone on the GIF activities with the advanced reactor systems. With that, thank you so much, Jiri. Thank you so much, Alexei. I'm not sure if you want to add something, Alexei.
Thank you, Jiri and Patricia. This was, I think, a great example of how interesting can those ETWG webinars be, and I hope everyone enjoyed it. Please join us for the next one, and thank you again.
Thank you. Goodbye, everyone. Thank you.
Thank you. Goodbye.